and this section is very important for you to understand how we normalize big data, and which is pretty simple. And then we're going to get to obtain very nicely well-defined error functions and all these cost functions and loss functions. This is one of the pretty simple equations for us to normalize the parameters based on maximum and minimum values of the big data. So this is the normalized data, and this is the parameters that you want to normalize. This is normalized data, and this is one you normalize. And x max, x minimum in the bottom right there, in the denominator right there, is the range of big data sets, and which is maximum and minimum, the ranges of big data sets at each parameter. For example, if you have a B and D and epsilon, you're going to have all the maximum and minimum values, all these values, and they are going in the bottom right there. So this is minimum, and this value is going right there. And y max, y minimum, y maximum is the range that you want to normalize your big data into. So you want to get all these big data normalized in between -1 and 1. Then y max should be 1, and the y min should be -1. For example, we have a couple of very simple data here. You're gonna normalize the data between -1 and 1, and you're gonna have a data range before normalization between 0 and 100, and you want to normalize the 50 and see how we're going to do that. So that here y max minus y min, therefore 1 minus 1, it is plus 1, right? So this is the range that you want your big data to be normalized into. So that's this value, and the denominator is the range of the big data before normalization. So that's 100 minus 0 according to this range is over there, and this is what you normalize to get this. So you put the 50, this is raw data before normalization, and minus 0 is same as this one, as I said, and your plus y minimum is minus 1, as you see, because you want to normalize between 1 and minus 1 over there. So all these calculations come up with the 0. So your normalized value corresponding to 50 under these conditions is 0. So 0 is between 1 and minus 1, which is fine. It is fine to me. And if you see a y max equal 1, y min equal minus 1, x max equal to 100, x min equal to 0, then 50. Then the 50, when 50, x equal 50, you're going to get a 0. This is x, this is y, according to this formula. And I'm going to say that you can use any variables to define these equations, but x and y is used for the parameters before normalization and after normalizations, respectively. And this is one of the simplest illustration of gradient descent. So you're going down and finding this point where your loss function becomes a 0. So this is your way to finding this point. So you need to have very nice error functions or cost functions. Now let's do one more normalization example here. We want to normalize P. It is a big number in magnitude of hundreds, thousands, compared to strains here, to river ratios, even compare with FC, which is compressed strength of concrete, and C over D and B over D. See, this is a pretty big number. So that we need to somehow make them look compatible for good error functions or cost functions here. So we need to take a look at the formulas here, and this is simply indicates that you need to understand and select a big data maximum and big data minimum right here in denominator. So big data maximums are here, this one, and big data's minimum is this one, I guess. Where? This one. Okay, so that denominator is here, and numerator is y max and y mean is a normalized range, which is 1 and -1. So you have this, and here you put here the data that you want to normalize. In this case, we take a look at this one and normalized, and we're going to put this as it is, and minus x minimum is same as this, right? The big data is before normalization, so this one goes here, and here plus y minimum 1 and -1. So we have here all the equation sets here, and to be minus 0.22297. So here this big data, which is 1071.9, shrink to this small data, which is minus 0.22297, normalized between -1 and 1. So this is B is normalized as a number between -1 and 1 from a 1071.9. So this is a procedures that we want to make all these numbers to be comparable, to be the size of same magnitude for making a good error function and cost function, so that your gradient descent is going to work very well. You're going to find the path, the best path to the location where your minimum error is found. Okay, now let's go and normalize one in strain, which is very small in magnitude, compared to the magnitude of what we have in B and D, right? Okay, now let's normalize one strain which is very small in magnitude. Okay, let's take a look at this one. Let's pick this one up to normalize, and when you normalize 0.0079, you want to put this in here. So this is the place for the big data that you want to normalize, 0.0079, and the rest of the numbers are here. In denominator here is the range of big data, and I found that the biggest number strain here in this big data, this is big data, selected big data, and small one is this one. So you go this, calculate it, and put them in the denominator. And again, here is same as x minimum here, this one, right? This one is same as this one. As is the formula right there. And then the plus y minimum, so y minimum is -1, right? And here again, y max minus y mean is this, because you are minimizing this between 1 and -1. So these are simple numbers. You got minus 0.6656. So this very small number now increases to a normalized value between 1 and -1. Okay, in opposite sense. And here B, as we see in previous calculations, the big number shrinked and normalized to come up with a small number which is between -3 and 1, whereas this small strain is increased to be normalized to become a number between -1 and 1. So that all this number right now, if you see here, all the parameters are well normalized. If you see, the B shrinks to small numbers all the way, D as well, but epsilon becomes large to be normalized 1 and -1, and also this becomes large, normalized between minus and 1, and all these things are right now calculated as normalized between this range, -1 plus 1. Of course, if you see the ranges, maximum and minimum number is always this, if you see. But even though you don't see a -1 and 1 here, but this is your range that you normalize, same all the way here. But the thing is that the mean value is not exactly 0 here, a little less than 0, because your big data is consisted of this statistics where your mean value is a little less than a standard, okay, which is minus 0.347, whereas this one D is close to 0. It's almost the mean value, the median value between -1 and 1, so that this can be a very well distributed in the middle of the big data, and also in the middle of a normalized data. And here this is quite a big in minus sense, and this is okay, very close to mean value and median value, or between 1 and -1. So this is what you get when you have a good normalizations. And now this well distributed numbers, big data input and output will get you a very nice cost function, or error functions, and all these functions will be used to calculate very nice gradient descent, and we will explain how to get gradient descent from a cost and error functions to go for a back propagation to update your weights and biases in few lectures. There's another example which I'll be publishing in future book. There we have a flying distance and the Lagrange optimization of flying distances, and this is the big data. I'm listing here 18 only, but I have like 1,000 big data over there to describe the trajectory of the cannon, as you see over there. And the big data, this big data is before normalization, and this big data is after normalization. If you see the data before normalizations, it's interesting to see most of the numbers well distributed between -1 and 1 here, all right, see, all 1 here. However, some of the numbers here is a little bit greater than 1, actually it's a lot greater than 1 for this variable, whatever they are, and this variable. So, and we come up with a necessity for normalizations. This is okay. This is okay, normalized already. So here, and you're okay too. So that, if we did not have these big numbers, if we only had these numbers and these numbers, then probably we wouldn't need any normalization, and that just the raw data is good enough for us to go and calculate the gradient descent. But we have this big number, we are disturbed by these big numbers, so that we can do that. We can do training and back propagation and calculate gradient descent before we go through a normalization right there, okay, here and here, okay. So we need to normalize this, and using the same technology that we learned, and go and normalize it. And in here we have all the numbers are normalized between 1 and -1 there, including these two columns here, so that all the numbers are right now between 1 and -1, so we can start a back propagation and calculating gradient descent, and try to update or revise the weights and biases. So you could say the normalization, initializations are very important, but you need to normalize yourself many times, but the initialization are based on default value here, as I explained in previous lecture. I'll take a few seconds to explain how to do with the MATLAB. MATLAB has a little commands for normalization. For example, this is the commands from MATLAB. Map min max. This is a MATLAB commands. Then your data will be automatically normalize using this commands here. So you are defining how many parameters are gonna normalize here. You define 9 and you go for all 9 parameters. So you're going to use a map min max commands to normalize. 9s are here, BD and all the way. This is 9, as you see in previous big data. This is 9 of them, right? So what you're gonna have here, you don't have to use your formula to normalize. The MATLAB will do normalize how many data you have, how many parameters you have, and just you ask them to print table, 2 tables, one for before normalize and one after normalize. This is before normalize and one after normalize, and you finish and display the time as well. So when you do this, the table before normalize and after normalize, you saw here. So this is the table before normalization, and this is table after normalization. It's just printed by the MATLAB map min max commands. Very easy and convenient.